We've got section 6.5 and 6.6 left in this chapter. And they both have to do with solving triangles. And 6.5, the technique we're looking for, is called the law of sines. Now, your author has a proof of this in your book, but it works out pretty nicely when you've got a triangle like this. So I'm going to label these angles A, B, and C, and I'm going to label their opposite sides A, B, and C, lowercase. So when you've got something that's got a nice right triangle in it, you can use what we've used in the last couple of sections. But if it's not a right triangle, we're going to need something else. And let's make this C a little bigger so we know which one's capital. We'll make this C a little bit smaller so we know which one's lowercase. And there's a nice relationship between these angles and their opposite sides. And it turns out sine of angle A divided by its opposite side is equal to sine of angle B divided by its opposite side is equal to sine of angle C divided by its opposite side. So if we give you some information about a triangle and it's not a right triangle, but you're still looking to solve it, you're still trying to figure out what the remaining sides and angles are, the law of sines can be a really nice tool. Now notice that I wrote this with the signs on top, but there's no reason I couldn't also write this as A over sine of A, B over sine of B, C over sine of C. Whatever's more convenient for the kind of calculation we need to do. So let's look at a triangle. And I'll label, let's see, let's get this side length 5. And we'll do this as 50 degrees, 60 degrees. Now, I certainly can figure out the third angle of the triangle. If I've got two angles, the third one always is immediate because I know they have to add up to 180 or they have to add up to pi if I'm in radians. So I'm going to get 70 degrees there. And label those two sides A and B. So I've got a few pieces of information. From the law of sines, I know that sine of 60 over 5 is going to be equal to sine of 70 over A, which is going to be equal to sine of 50 over B. Follows from the law of sines that we had on the other page. And now it's just going to be a little bit of algebra. We end up with A equals sine of 70 times 5 over sine of 60, and B sine of 50 times 5 over sine of 60. Again, in degrees in this particular case. And this works out to about 5.425. And in this case, it's about 4.423. Remember, we're in degrees. If you're not getting an answer that matches my example, check to see whether or not your calculator is in degrees or radians. It definitely matters. Now in this case, we had two angles to start with, which immediately gave us the third angle. That's not always what we have. If I was looking at this triangle, so let's go with 6, 3, pi over 3. So previously I had one side and two angles. Now I've got two sides and just one angle. So I still should be able to use law of sines, but I'm not going to be able to preemptively figure out what all the angles are. So let's call this guy capital A, this guy capital B, and this side little b. That should help keep things in check. So, law of sines, sine of pi over 3 divided by 6 equals sine of capital A over 3, sine of capital B over B. So, this I know and can compute directly. This I know part of, and this I got nothing. So sine of pi over 3 over 6, that's going to be square root of 3 over 2 divided by 6, so square root of 3 over 12. And we're going to set that equal to sine of capital A over 3. So sine of capital A equals 3 square root of 3 over 12. So A is equal to the inverse sine of 3 over 12, which is about 0.448 radians. Now we're going to need to approximate B, because B is going to be pi radians for the entire summation of the three angles in the triangle, and I'll subtract off the pi over 3 from this angle. I'll subtract off the 0.448 from this angle, and the result should give me B. So pi minus pi over 3 minus 0.448, and I get an approximate value of 1.646 radians. Now, if I want, I can use that to find little b. That's the only piece that's still left. This guy down here, which was the length of this missing side. This we've already computed, square root of 3 over 12. This we've already computed, about 1.646. So let's plug and chug from there, and you will end up with B, again, approximate. It's about 6.908. Now, the last example was in degrees. This example I kept everything in radians. So again, be aware of which ones of these you're working with and make sure that you are comfortable switching back and forth between degrees and radians depending on the information that the problem gave you. Unfortunately, this doesn't always work. So, suppose I had a triangle A, B, C, little angles A, B, C, and I claimed that little a was 10, little b was 15, and capital A was 75 degrees. Now it's possible for me to show that this can't possibly exist, because if it did, sine of 75 over 10 would have to be equal to sine capital B over 15, which would mean sine of B equals 15 times sine of 75 over 10. But if you actually compute that, that's about 1.449. Well, why is that a problem? The sine function has range from -1 to 1. The sine is never bigger than 1, and it's never less than -1, no matter what you do. So any triangle with these measurements, it's not a triangle. So kind of another cool application of the law of sines. You can actually use it to show that in some cases, some measurements just will not make a triangle, no matter what you do. So work through the homework, practice those. We'll have law of cosines up in the next video.